Welcome back to the deep dive. So today we're going to get into something pretty fundamental to Kubernetes, the communication layer.
Right, how everything actually talks to each other.
Exactly. We've talked about the architecture, the pods, the nodes, but not how all these moving pieces connect reliably.
And that's the key word, reliably. This is the core of Module 3, and it gets at what you could call the Kubernetes paradox.
The Kubernetes paradox. Okay, I like that. Let's unpack it.
Well, we know every pod gets a real unique IP address. That sounds stable on the surface.
Sure, an address is an address.
But the whole point of Kubernetes is that pods are ephemeral. They're disposable.
Built to fail, essentially.
Exactly. So your database pod has a memory leak. Kubernetes kills it, instantly spins up a replacement. But that replacement gets a brand new IP address.
And if my front-end app was talking to the old IP, the connection is just gone, snapped.
Gone. Instantly. And this is happening all the time with scaling, with updates, with failures. You're trying to connect to a constantly shifting list of addresses.
So we need something that doesn't shift, an abstraction layer that provides stability.
We need an anchor. Something that has an address that never, ever changes.
And that anchor is the service resource.
That's the one. The service is the backbone of all this. It solves the problem by giving you two crucial things.
Okay, what are they?
First, a static IP address. It's called the ClusterIP, and it stays the same for the entire life of the service.
And second,
a corresponding stable DNS name. So now, your applications don't need to know about fragile pod IPs. They just connect to the service name, like database prod.
so it's basically an internal load balancer then? But how does it know which pods to send traffic to if they're always changing?
This goes back to something we've touched on before, labels and selectors.
Right, the key value pairs.
Exactly. When you define a service, you give it a selector. You tell it, I want you to find all pods with the label app.database. The service then constantly watches the API server.
And it builds a dynamic up to the second list of all the healthy pods that match that label.
Precisely. So your front end connects to the stable service, and the service just forwards the request to one of the healthy pods on its current list. It handles all that routing magic for you.
That makes so much sense. It's like a permanent receptionist for an office where the employees are constantly changing. The receptionist's phone number is always the same.
But they always know exactly which desk to forward the call to. That stability is what enables things like zero downtime rolling updates. The front door never changes, even while you're swapping out all the furniture behind it.
Okay, so that nails internal communication. But eventually, we need to let the outside world in. We need to expose this to our users.
And how we do that defines the type of service we create. There are three main types you need to know.
Let's start with the default, which is ClusterIP.
Yep. The name really says it all. It creates an IP that is only reachable from inside the cluster.
So this is purely for internal traffic.
Purely. Think about your monitoring systems, your message queues, a private API, anything that should absolutely not be exposed to the public internet. It's the most secure, most common type for internal components.
Okay, but what if I'm just developing something? I need to hit it from my browser quickly, do some testing, but I don't want to set up a whole production level thing.
That is the perfect use case for the next type. NodePort.
NodePort. So this opens a port on the node.
On every node. It's a really interesting mechanism. It picks a high-numbered port, say 322.2001, and opens that exact same port on the external IP address of every single one of your worker nodes.
Whoa, okay. So if I have 20 nodes, all 20 of them are now listening on port 32001.
Correct. And if you send traffic to any of those node IPs on that port, you'll get routed to your service, which then load balances it to your pods. It's a quick and easy way to get external traffic in.
It sounds a little clunky for production, though. A user shouldn't have to type in mysite.com.32001.
That's the first problem. The second is that you're tying your access point to the IP of a specific node. And nodes can be ephemeral too.
Right. If that node goes down, that access path is dead. So we need a true, stable, professional front door.
And for that, we bring in the big guns, the load balancer service type.
This is the production standard, especially in the cloud.
Absolutely. This is where Kubernetes gets really powerful because it integrates directly with the underlying infrastructure provider.
So what happens when I create a service and set its type to load balancer?
The cluster's cloud controller manager sees that request. It then makes an API call out to your cloud provider, AWS, Google Cloud, Azure, whichever, and says, hey, I need you to provision a real external network load balancer for me.
So Kubernetes is literally telling AWS to spin up an elastic load balancer.
Exactly. The cloud provider creates it, gives it a permanent public IP address, and then feeds that IP address back to Kubernetes, which attaches it to your service object. Now you have a single stable public IP on a standard port like 80 or 443.
That's incredible, but I'm guessing it's not free.
It is not. That's the main catch. Every time you create a load balancer service, you're usually provisioning a dedicated paid cloud resource. If you have 20 apps and you expose them all this way,
If we're paying for 20 cloud load balancers, that bill could get high fast.
very fast.
Yeah.
Which is why you have to be deliberate. This leads us to the next logical problem.
Which is what?
Services are great, but they operate at layer 4. They deal with TCP and UDP traffic based on IP and port.
Okay. Connection-based.
Right. But what if I'm running a website and I need to route traffic based on the URL? I want an API service and blog to go to my blog service? A simple layer 4 load balancer can't do that.
It doesn't understand HTTP paths. For that, you need layer 7 intelligence.
And for that, you need a different resource entirely. You need Ingress.
So Ingress is the specialist for smart HTTP-based routing.
It's all about consolidation and rules. You can have one single external load balancer, one public IP for your entire platform, and then use Ingress to route traffic to dozens of different back-end services based on the request.
Can you give me an example of a rule?
Sure. You could write an Ingress rule that says, if the incoming request is for the host name api.myapp.com, send it to the AP service. If the path is images, send it to the image CDN service. Everything else, send it to the main website service.
That's way more powerful. But there's a really important distinction here that trips a lot of people up, right? Ingress is not a service type.
It is not. This is critical. An Ingress object is just a set of rules. It's a blueprint. By itself, it does nothing.
It's just a definition. It needs something to actually enforce the rule.
Precisely. You need a separate piece of software running in your cluster called an Ingress controller.
Like NGINX or traffic.
Those are the most popular ones.
Yeah.
That controller is the thing that actually reads the Ingress rules and configures itself to act as that smart reverse proxy. Without a controller installed, your Ingress objects are just ignored.
So, to sum it up, service is for stable identity and layer 4 load balancing. Ingress is for complex layer 7 HTTP routing, but it requires a controller to do the work.
A perfect summary. But now we have to connect it all back to the core architecture. All of these services, Ingress rules, they're just configurations stored in the API server.
They're just a desired state. How does that state become a reality on the network itself?
That is the job of one of the most critical components on every single worker node. The Kube-proxy.
The traffic cop.
The ultimate traffic cop. It's a process that runs on every node, and its only job is to watch the API server for changes to services and their endpoints.
So when I create a new service,
the Kube-proxy on every node sees it instantly. It then reaches into the node's operating system, into the Linux kernel, and programs the network rules to make that service work.
how does it do that? What is it actually changing?
Traditionally, it used a technology called iptables, which is essentially a set of firewall rules. It would create complex chains of rules to say, if you see traffic for this service IP, forward it to one of these pod IPs.
I've heard that can get slow in really big clusters, though.
It can. The number of rules can explode, which is why many modern clusters use a different mode called IPVS, or IP Virtual Server.
Then what's the difference?
To put it simply, IPVS is designed for load balancing from the ground up and uses more efficient data structures, like hash tables, in the kernel. This makes it much, much faster at routing traffic, especially when you have thousands of services.
So the service is the declaration, and the Kube-proxy is the enforcer, constantly updating the low-level network rules on every node to match that declaration.
That's the beautiful synthesis. The declarative model meets the operative reality in real time across the whole cluster.
This has been a fantastic deep dive. Let's just quickly recap the main takeaways for you listening. First, the service resource is your anchor. It solves the problem of pods being ephemeral by giving you a static IP and DNS name.
Then we have the 3 service types. ClusterIP is for internal-only communication. NodePort is for quick and simple external access. And LoadBalancer is the production-grade standard that integrates with your cloud provider.
And for smart, layer 7 routing based on HTTP paths and host names, you use the Ingress resource. But remember, it needs an Ingress controller to actually do the work.
And finally, the unsung hero that makes it all a reality is the Kube-proxy. It runs on every node, watching the API server and programming the kernel's networking rules using iptables, or IPVS, to enforce the state you defined.
It really hammers home that Kubernetes networking is less about packets and wires and more about definitions and constant enforcement.
I think that's the essential insight, really. When you create a service, You aren't configuring a network device. You're making a promise of a stable destination. The true complexity and, frankly, the magic of Kubernetes networking lies in the relentless, invisible work done by components like Kube-proxy to uphold that promise 24/7 across an infrastructure that is designed from the ground up to be chaotic.
That's a powerful way to think about it. We hope this helps you navigate Kubernetes networking with a bit more confidence. We'll catch you on the next deep dive.